Okay, cool. Thank you very much for hosting. This is Alan from Brevis. I'm going to tell you a little bit about our recent work, an exciting piece of work, a modular performant zkVM called Pico. So we all know that blockchains are viewed as the world computers. They have like so many good features like decentralization, consensus, all these kind of stuffs. But if you think about it, if every kind of computation is going to be happening on chain, it cannot run faster than a single server. So this is actually the bottleneck for the blockchain. So to actually massive scale up the throughput of the blockchain, we at Brevis actually considering all the kind of things that is related to the off-chain verifiable computing. So this is our main theme of the company. So imagine that whenever you're going to be integrating or like interacting with the blockchain will not do all the kind of computation on chain, but instead it will offload some kind of complex computation towards Brevis, and then the Brevis will actually do the computation off chain. And then usually it is kind of it might be enough to just send back the results to the blockchain. But the thing is, like, the blockchain has to verify that this result is integrated. So which means like at Brevis, we also not only just compute the results, but also generate the zk proof corresponding to that, and send both of them back to the chain. So basically, on chain we will do the verification of the proof. I think the screen just dies. Okay. Sure, no problem. So I'll just go slowly. Okay. So if we view the whole picture of that, is just the blockchain working as the glue point of the verifiable off-chain computation right here. You wanna? Oh yeah, there you go. Thank you. So as I mentioned, the blockchain is actually working as the verification layer, or actually we call it the glue point of verifiable off-chain computation here. So our first product, which is our zk coprocessor that deal with the computation of data access, has already launched last year, and it was a great success. So basically what it do is to generate a zk proof of arbitrary computation on any historical on-chain data. So it can be applied to many kind of different applications and apps and projects. Here, just to name a few. For example, we are collaborating with the PancakeSwap, QuickSwap for their some volume-based rewards or some kind of these kind of problems. Euro as well, the rising star in the stablecoin for their continuous reward thing. So basically, we utilize the computation results on chain in a trust-free way. So we just send back the zk proof, and then the on-chain projects or contracts could actually make use of it. So during the collaboration with many of the projects, we actually figure out that, okay, our zk coprocessor is doing a great job in terms of dealing with the complex logic for data access. But the thing is, like, verifiable computing actually goes way beyond just the data access, right? You may have like more complex business logics. You may want to do some kind of real-time Ethereum block proving. You may want to do some verifiable AI inference. And since the AI model is just too large to actually run it on chain, you may want to do it off chain and then just do the verification on chain. So we can see the generalized computing scenario here. And if we really want to support all of them, we need to democratize zk. Then there might be some other ways, some other solutions to do that. So currently we have two kind of solutions. One is the zk coprocessor, as we have been doing at Brevis before. So the advantage of it is it is just blazingly fast. You can view it as just a set of like handwritten circuits. It is super fast and efficient to be used. And then, but the thing is, like, it is mostly focused on applications, specifically the application that needs the data accesses. So sometimes for other kind of application that focus on other aspects of the computation, it may not be the best choice for that. And also, like for developers, it may cost more developer time and effort to actually do the development. So the other case or the other possible solutions is to use the so-called zkVM, where developers just write plain raster code, and then all of this raster code will actually be translated into a circuits and then proved to generate a proof that is verifiable on chain. So you can see that it is highly flexible. It is also easy to develop because you just deal with plain Rust. But the thing is, like, usually it will cost a huge overhead, performance overhead here. So you can see that we are uncovering the challenges that is faced by democratizing zk. So the key to that, the key challenge here is that we are unable to balance between developer time, security, costs, performance, and etc. and etc. And one thing that I didn't mention in last slide is that we also need our system to be adaptive towards fast evolving zk theory. So starting from the 1980s, zk theory has seen a massive emergence of new protocols, new theories coming out every single year, especially for the last 3 to 4 years. That is say that either zkVM or zk coprocessors, a one-size-fits-all solution will be inherently limited. All right, so 3 points here. What is the good solution? First thing is it has to be performant. Otherwise, there's no point for using that. Second thing is it better need to be developer friendly so that we can just do any kind of computation by just using that. And then you can basically see that zk coprocessors and the zkVMs are the endpoints of this kind of big spectrum. That is basically trading off between these two parameters. And for the third one, the flexibility and being future-proof, it is usually ignored by any of the existing solutions. So which is why, like, we try to build ourselves a modular performed zkVM that tries to solve all of these kind of challenges. So first thing is that the Pico is very flexible and being future-proof. It has the modular architecture that allows you to easily change between different proving backends. I think we are the first zkVM that actually supports this kind of great feature. And later I will tell you more about it. And also it supports the customization for proving workflows. So usually when we bump into either zkVM or zk coprocessor, the current solution actually are mostly one-fits-all solution, which doesn't really allow you to do such kind of customization of the whole proving workflow. And we at Pico are able to enable that. And second thing is, of course, it is performant. It is performant not only because of the current architecture that we are designing and implementing, but also because that we are offloading heavy computations towards various zk coprocessors. And these zk coprocessors could be function-level zk coprocessors, also known as the precompiled chips. They can also be application-level zk coprocessors, as we have mentioned before, the data access coprocessor developed by Brevis in-house. Third thing is that it is also developer-friendly. We can just write applications in plain Rust. You basically can develop anything that is zk native with zero knowledge about zero knowledge circuits. And also for the program that is very large, arbitrary sizes, we can do that via continuation. So basically to chunk the huge program traces into several chunks, and then prove each of them, and then combine them to the one that is on-chain verifiable. So as I have mentioned, Pico is able and designed to be flexible in proving backends. And currently we are supporting many of them, including the Stark on Koala Bear, which is our default choice, Stark on Baby Bear as well. I think many of the current zkVMs are actually utilizing this kind of this prime fields. And it turns out there's a subtle trade-off between taking the Koala Bear versus taking the Baby Bear. as your primary field for doing stock. And we are also trying to support a circle stock on Merchant 31. And then you can see on the right-hand side that if you are going to be just changing your proving backends, you can do that with only one line of code changing. So you can just set your clients to be, say, either Koala Bear, Baby Bear, or Merchant 31. And then for all the rest of the code, they all just stay the same. So I think this is the breakthrough thing that we are supporting. And imagine that you have an application that you don't know which kind of proving backends that is best to you. You can just switch back and forth and test what is the best for your application. As I mentioned, like there are actually trade-offs or like a sort of differences between Koala Bear and Baby Bear. At the first glance, you may think like, okay, this is pretty easy because they are kind of similar. But the thing is, like, they're quite different in terms of implementing all the corresponding circuits. So it actually needs a huge engineering effort as well as the design to actually enable both of them at the same time. And especially for Koala Bear, it has very good advantage in terms of recursion circuits. It has a very efficient recursion compared to the Baby Bear, which is why we set it to be our default fields. What is more, Pico is designed to be customizable. So usually you will bump, for all the zkVMs, you will bump into the so-called proving workflow, where you first start with your RISC-V program, and then at some kind of phase, at the first phase, you are going to be in Pico, you are going to be translating it into a RISC-V proof. And then after that, you are going to be converting that RISC-V proof to a recursion proof. And since we are doing continuation, we may have like multiple different recursion proofs, and you're going to be using the combine instance here to combine them into a single recursion proof. And after that, there can be some kind of options, including that you can do the compression of the proofs or embed the proof into a starkly verifiable fields like a BM254. And also, finally, you're going to be having this constant size EVM verifiable proof. So this is the default working workflow. But the thing is, like, you can just do the plug and play. For example, you have like a smaller program every time you're going to be run. So you don't have to do this kind of combine, because every single time you're going to be only having a one chunk or one segment of the whole program. So there's really no need to do the combine. And sometimes you don't really care about the compression of the proof size, but really you care more about the latency. Then you can just eliminate the compressed space, and then it is also good to go. So this is actually providing a huge advantage in terms of customization, specifically for different kind of applications. And then what is inside in each phase is what we call the instances. So for each of the instances, you're going to be having its own proving backends, its own circuits or chips, and its own proving processes that is supporting different phases functionality. All right, come to the, let's get down to the concrete numbers. Pico is by far the fastest zkVM on CPU. So we are benchmarking against the various zkVMs, including RISC-0, OpenVM, SP1, all of which are supporting this recursion and the snark verification. And then also we are benchmarking on different workloads ranging from the artificial smaller ones like a Fibonacci towards more real-world larger workloads like a Tendermint Light Clan, or proving simply an Ethereum block. Here we proved the block number with 171, 06222, which costs you about 10 million gas. And then again, like we are benchmarking on CPU on AWS R7A, 48 extra large. We mentioned that we are doing no optimizations in terms of compiler for any of the zkVM. We are also using any of the zkVM, their default parameters, to just do the plain run to actually see what is the gap between each of them. So as you can see that we are at least more than 70% better compared to the second best among all of us. So basically means that we are actually the best either in smaller or larger workflow, at least on CPU. And talking about GPU, as Ouyang have said, GPU might be the end game for the performances of the zkVM. We are working on that, so hopefully that will come soon. So hopefully I have already convinced you that on CPU proving by itself, it is already the fast one. But the thing is, like Pico is not only that. Pico is actually pushing the modularity to a new level. So as you have seen that many other zkVMs, where it is built on a RISC-V ISA or some other ISA, it is including or integrating with a functional level precompiles like cat, check, hash, shu, Poseidon 2, SHA-2, all these kind of precompiled cryptography operations. But the thing is, like Pico is doing way beyond it. So we are able to easily integrate with application level coprocessors. It could be some kind of on-chain data access ZK coprocessor. It can be zkML, or it can be some other application-specific ZK coprocessors. That is to say that we are essentially implementing this glue and the coprocessor architecture that is actually mentioned by Vitalik not very long ago. So basically, whenever the users or developers are interacting with the Pico here now working as a glue, which itself is including many kind of cryptographic hash functions as the function level ZK coprocessor. At the same time, it is not actually doing all the computation by itself, although that is also an option. But I'm here to say that that is definitely not the best option. So here, what we do here is to let the Pico to offload again some of the very complex application-specific circuits or computation towards those ZK coprocessors. That is a setup for very efficient handwritten circuits. So again, it can be like on-chain data or zkML and other kind of things. And then in this way, we are able to make it very application-specific because at Brevis, we are actually very application-oriented. So we care more about concrete applications that can take advantage of their own property of the computation while being very general at the same time. So a little bit of the heads up on this this comparison. As I have mentioned, like we can do that. We can do anything, just writing plain Rust code, just and then apply it to any kind of zkVM. And here we are using Pico since it is already the fastest. But for this kind of specific application, proving trading volume of 4096 trades on Uniswap, it takes a lot of time, and it is also very costly. And then if we're going to be integrating Pico with ZK coprocessors boosted, and then we are able to achieve more than 30 times of performance gains, and then about 2/3 of cost cuts. So this is pretty impressive, and note that this is also the very beginning. And we are actually now integrating, we're actually doing multiple things. The first thing is, of course, to optimize the zkVM, the architecture. And second thing, we are also integrating with different ZK coprocessors to work on different applications. So if you are interested, please come to visit us on Pico repo or doc or our websites. Please come to build with us. Thank you.
Thank you so much, Alan.